right, good morning, everybody. It's 9:10 according to my watch, so we will start. Welcome to class. Welcome to this Wednesday, October 14. We are going to have the third and final lecture on linear regression, linear models. And we started this discussion on Friday last week, had part 2 on Monday, and this will be the concluding one. And this is a series of things that we needed to have in terms of the theory behind or the concepts behind, but I'm going to dedicate Friday's class to do a lab session in the sense of walking through code or see examples, and it will be more tailored towards R. So we will complete the linear regression discussion lecture-wise today, and then we'll have code or examples of how to implement these things and how you use them in R, and I'll make some side remarks on Friday. And this will complete our discussion on linear regression in general about regression, and then we will move on to classification next week. This is also a time where we have completed the first 4 assignments. For those of you who are in 475, I have submitted your midterm grades yesterday evening. And this is, as I have told you, an average of your performance on the first 4 assignments, including the 4th one. So Helen spent some time and did a good job completing grading assignment 4. And so it's taken into account in calculating the average and determining your midterm grade. 575 students. Your assignment 4 is not graded yet. It will be completed, but it will be posted for everybody when all of them are graded, not just 475. We don't have a way to separately post this and post that. So wait until you get there. For those of you who are 475 students, this will be a good moment for me to remind you what midterm grades are. You are all seniors, or you've been around for quite some time, so you know what midterm grades are. But I want to remind you in our particular context what it means and how you should interpret it. First thing to know is that this is your average performance on the first 4 assignments you did. That's what we have done in terms of evaluation so far, so it makes perfect sense. We are talking about linear regression, and I use the term predictor all the time. I don't want you to have this as misunderstood and as a predictor for your final grade. Why? Because you have more things to come. You have something that was 40%, that's the project, and then 20% that will be the late midterm exam. So you've got 60% ahead of you, and so this will be 35%. And out of that 35%, you've done 4. The 5th one is yet to come. I'll talk about that in a second. And therefore, understand it for what it is. But the first thing you should do is celebrate. Celebrate that you have accomplished 4 assignments. And as a class, I am very pleased with how you did. The assignments are not of the same complexity and difficulty as a project. They are not as the same complexity and difficulty as what a midterm exam would be, but they are taking you sometimes, and I know they are challenging. So the fact that you've done well is due to you. It's something to celebrate, but I also want you to understand it for what it is. All right, 575 students, you don't need to have midterm grades, but you know where you are, and when it is finished, it will be reported. You convinced me on Monday to extend the deadline for submitting project proposals, and I did, and it is today, but I know many of you have started submitting, and so use the time for those who need it, who convinced me to do the extension, and I know that you may need that, and so do that and complete. Once I have seen everything, then I will start looking through them and approve or not approve. I have sampled 5. I have sampled 5 and looked at what your projects were, people were saying. Out of those 5 I looked at, there was none that I would say I would reject. So that if this is a good sampling, if this was an election poll and I have sampled 5 people at random, this would tell me this thing is going to be something that will turn out to be approved. I cannot say that for sure. I have to see the rest of them, but I could say that the ones I have seen were worked out that way. This brings me to today's warm-up question. And it is going to be a little bit complicated. So I'm not going to burden anybody by having to write a complicated warm-up question. And so I will write it. So I will have the honor of writing it. And it's going to be to just give me an idea about how you feel about the project you proposed. And so I'm going to say how excited, and I'm going to give you options, and that's why I'm writing it. How excited are you about the proposal, project proposal, that is? Okay, and you have 5 options. One is very excited. Two, moderately excited. You can start thinking about them, but I want you to have, and you will answer just the numbers because I don't want you to type. Just excited, nothing more. And then the fourth one will be not really that excited. And this is not evaluation, you know that what I mean, not really that excited, is the fourth category. And the fifth one is, I just had to go with something. I had to go with something. And therefore, this is what I submitted. Because you asked me to submit a proposal, and I did. I had to go with something. Otherwise, it's just, had to go with something. Okay, these are your 5 choices. Very excited, moderately excited, not really that excited, and had to go with something. And go ahead and tell me how this one is. As I said, I would like to know how excited you are really, and the project proposal doesn't. It's very objective. I ask you to tell me what it is, what your plans are, where you'll get your data, and things like that. There were very specific things that I have asked you. There was no place for you to express that, and I would like to know. And this does not mean much in terms of me approving it or not approving it, but it will give me a good sense. Sorry, it was not ice cream topping type of warm-up question, but it is a warm-up question nonetheless. So go participate, and we will start our discussion today. So what we are going to be doing today is extend this idea of linear models. Linear regression is what we have called it. And I'm not sure if I have told you, and I'm not sure if you have ever wondered why this thing is called linear regression. A linear model would have probably been a better term. And it has got historical reason for it. And sometimes we've got them historical reasons that make the existence of something possible, and they get stuck with us and we will use them. So regression to the mean, if you have not heard of it, Google and you'll find that's kind of where this thing is coming from. Regression to the mean. And so we keep calling it in that sense. But we are working with linear models, and that's what we did for the first 2 lectures. And we saw one way to extend it. The one way to extend it last time we saw was when we have variables that are, these are predictors, when we have variables that are not continuous, qualitative variables, and they would have categorical values to them. Are they troublemakers for us, was the question. And we said, no, we can handle them. We can handle them by having dummy variables, and we will say 1 and 0 when something is on and off, or something is this or not this. By having to model it that way, we can continue to do what we were doing with linear models without any trouble. And we saw how to interpret them. And we extended that to say, okay, we have got many of them. I've got not just one categorical variable, but I've got multiple of them. And we say we can handle that too. And so we would need, if there is something that has got by levels, not categorical values, different ones, because they would be handled the same way. We will have one dummy variable for each one of them. But what I meant to say was when you have a categorical variable that has got many levels than 2, it's not just on and off, that's enough. And so we would use k-1 dummy variables to capture them. And the ethnicity example for that credit card data set was a good example, and we saw that. Today, we are going to see 2 ways in which we would extend. Qualitative variables are fine. Dummy variables will handle them. The 2 extensions we'll see today are interaction and non-linearity. Non-linearity is not a surprise. The world is not linear. We know that. And of course, in fact, there isn't many things that are linearly related. And so how do we do when all we have is a linear model? I told you last time we can handle this, and it is kind of counterintuitive, but we will see how we can capture non-linearity. That was the second one. The first one is already introduced. I already introduced it when we started discussing linear regression the first time we met on this topic, and that was Friday. I told, we had that advertisement example, and you were a consultant, and I told you, there were questions to pose, and one of the questions was if there was interaction or synergy between the variables. That is what we will start off with today. So 2 extensions. One has to do with interaction, the other has to do with non-linearity. We'll start with interaction, and we go back to that same advertisement data example we had. And just as a reminder, we've seen it many times now. This is a situation where we are investing in advertisement on TV, on radio, on newspaper, and sales is what is to be predicted, the output value. And so the model, the linear model we have, look like when all of them are combined, multiple linear regression, the subject that we had last time. When all of them are combined, we'll have an intercept and we'll have a coefficient for each of these media, beta 1, beta 2, and beta 3. And this is how the model would look like. This one, we were careful last time how to interpret them. As opposed to simple linear regression, which would take one predictor at a time, ignores the other ones, this one has taken them all into account. The way we would interpret the beta coefficients was if in the presence of radio and newspaper, beta 1 is the coefficient or the way in which TV advertisement gives dividend to sales. If you increase this by this much, we'll get that much. In the presence of the others, when they are fixed is what we were saying. And so the other beta 2 and beta 3 would be interpreted the same way. But there are times when things are not like cleanly separated in this way. And this particular example actually shows that, where you would see some interaction. The way the multiple linear model was shown with that mathematical equation, including how the betas were calculated using least squares, would make them be independent in that sense, that they are contributing in the presence of the others, but when they're fixed, here is where their contribution comes. But there are times when predictors, variables, would have synergy between them, something that would make them work better because they are together, and will have something that will be better than having one thing dedicated to one of these media. In this particular case, if you had $100,000 to invest, would you be better off having half of it on TV and half of it on radio, or having the entire amount dedicated to one of these two? If there is something to be gained by having to have two variables interact or have synergy between them, synergy is a good term to use, and you probably know it from its dictionary meaning, but think about when you have two people work together and they would produce more than what they would have done if they were just to sum it up. Your projects are actually a good example for that. Don't think of your partner, the person you will be working with. Most of you will be working in a team of two, to say, I am doing half of the job, the other person is doing half of the job, so we complete 100%. It's not only that, you would actually do more than 100% because you are working, you are bouncing off ideas, you're synergizing. And so this is similar to this idea here, but it'll be mathematical, it'll be more quantitative. Last time, when I looked at this example and we looked at how the coefficients, the beta 1, beta 2, beta 3 were computed, I told you that the least squares is the fit. And when it was a single variable, it was a line. And when we have more, it will become a surface of hyperplane. In this case, this is the hyperplane, the green one that you see, that gave us to the best fit for these data points. The red points are the data points. And I'm having now forgot the newspaper because, as you remember, it was not actually all that great. It was not a great player in terms of increasing sales. Let's pick the two that are good. Investments in TV and radio were the ones. And so if you were to look at the fit that has got these three coefficients, and the green one will show them, and the data points are as you have seen them. So we're seeing this a slightly different way than what we saw last time, but we've basically seen a similar picture before. But the point I want to make now is different than what we did before. Generally speaking, if we were to minimize the residual sum of squares, all of the errors that you can make, this surface is the best fit. That's why it became the linear model. But if you observe how the model is behaving in how the values are distributed between TV and radio, the amount we spent on advertisement, and how the model is doing in terms of capturing what the real data is, there is a pattern that you would see. If you go to the kind of extreme points of the hyperplane, the points are above the plane. If you see some other places, the points are under it. Whenever the points are above the plane, it means the model is underestimating it. So they were higher, but this is what our model does. This is because when the money is split roughly, not necessarily equally, but in some good proportion that comes close to to the two of them being of equal amount, there is a synergy that came, and therefore there was more sales, but our model was not capturing it. So you get a clue that there may be something that's going on with interaction here that may be benefiting. And that's exactly what you would see in the picture. And the place where it's underestimating it is because it's not capturing the interaction that exists between these two predictors, TV and radio. Now, that was a motivation. So now we are going to do it. And I told you that this is mathematical, and so we could do this. So we had three predictors: radio, TV, and newspaper is all we had. And so we would expect three coefficients to happen. For the purpose of the discussion I have now, we are going to focus on, we'll ignore the newspaper and think of it as if we had only two. So when we want to capture interaction, synergy between variables, we would introduce a third variable that was not there, but it will be our making. And our making will capture the thing that we thought the interactions are happening, in this case, TV and radio, and we'll literally multiply them. These are numbers, as you know, they are quantitative values actually. And so multiplying them would make sense. So we multiply this and create a new variable. And that new variable is now the one that is going to account for this interaction. And it will get its own coefficient, just like TV and radio had. TV had a beta 1 and radio had a beta 2. Now the new variable corresponding to this interaction will get a new coefficient called beta 3. So now we have a new model that has, originally our data set had 2 because we chose 2. We ignored the newspaper, but now we are pretending as if we have 3, and the third one is coming as a product of the first 2, or the 2 that we thought were having interactions. If we do this and feed it to our model and see what results we would get, this is a result that R would have given us, which is what we will see on Friday, by the way. You should make sure that you'll be there to see how things are done. Consider it as a lab session in some sense. I mean, walkthrough of a code. We have seen this sort of lectures in the previous weeks before, so it's not completely new to you. And so we will see. And so if we were to get report on this, this is a summary, the table that you would get, and I have shown you a table of this kind in the last 2 or 3 lectures, the 2 lectures we have had. We will see values, p-values, and we will now know whether the betas that we are looking at or the variables that we are considering are strongly significant or not by looking at the p-values. And we see that the TV and radio were significant. We knew this all along, but the newly introduced one, the interaction between TV and radio, the product, is also strongly significant. In fact, it is very, I don't know if I need to say more than that. Strongly significant, that's what the p-value would tell you. So it's good to include it, and it would improve our model's accuracy. Remember the place where it was doing a poor job underestimating, now we'll get a better one. So the p-value here shows that compared to the null hypothesis, which would be beta 3, the coefficient for the interaction variable is 0, this one is significant, and therefore it has to be paid. If you are so good, which I know you are, and you would remember every number I tell you, which I know you do, we looked at a case where we looked at the thing when it was just TV advertisement, and we saw the R² value we got. It was something like 0.6 or something like that. And then we said, okay, that was just one. When we have all of them and we improved that, and it became 89.7 or 0.897, we said, okay, it was actually good to have all these predictors included in our model, and that's where we were. Now, by having to account for the interaction between TV and radio, TV and radio cells, we increased the R² value to 96.8. This is a great achievement. So we have actually now been able to explain even more of this variation, as I will show you in the next slide, because we have accounted for the interaction between them. And here is a mathematical way to say how well we did by having to do the interaction variables. So with it and without it, and we divide it by something that we would take out of 100, and 69% of the variability in sales that remains after the additive model, the one that has interaction, has been explained by this interaction term, is what we would say. And so here's a couple of bullet points that you would want to look at when we get these values. Now we have got beta 1, beta 2, and beta 3, they have values. If we were to see how much of a return you would get if you were to spend $1,000 on advertisement, you'd now see what it would mean that the sales on TV kind of depending on what you've done on radio, and vice versa, the thing on TV, depending on what you have done on radio, is numerically expressed in this way. These are just found by plugging in the numbers we got in the model. Okay, so interaction, when it exists, is significant for some data sets, and our model can handle that by having a very simple addition, and that was one of the interactions to do. So I've told you now how to introduce it. I've told you now how to assess it and to see that it is making a difference and things like that. Suppose you had this advertisement data set, you found things, there was interaction between TV and radio, and you got a p-value. Suppose you've got something similar for another data set, and the interaction variable you introduced was great. The p-value was small. It was strongly significant, and so you wanted to include it. When you go back to the parent, the thing that gave birth to these interactions, okay, forgive my language there, but the ones that where it was coming from, they may not be that significant on their own. And you may be tempted to say, okay, this TV alone was not that great, or the radio alone was not that great, but the interaction was really, really great. I need to include it in my model, and I'm going to drop one of those other ones, the parent ones, as they called. That's not a good idea. The hierarchy principle tells you, even if that happens, even if the things that gave to the interactions are not that significant, it will be very difficult for us to interpret them if we exclude them. And therefore, it will be a good practice to include interaction variables in your model. If you do that, to also include the ones where the interactions are coming from. And this has mostly to do with how you would interpret your results. Okay, that's called hierarchy. So be it. Okay, what about if we were to consider a situation where we are going to evaluate, or we're going to think whether a qualitative variable also has got something to do with interaction. So we saw two things now. The two things that interacted were sales, advertisement on TV and radio, and they were quantitative values. We just took a product, added a new coefficient to it, and that was how our model works. What if one of them was a qualitative one? Do we need to panic? No. So we could do exact same thing that we did before when one of the variables is a qualitative one, and we proceed in the same way we handled qualitative variables when we were not looking for interactions. What we did there was to introduce dummy variables. And by having those dummy variables, we would see whether we would proceed with our model, and there was, the baseline and difference from a type of interpretation we gave. Exactly the same or very similar idea could be extended now. And for this example, we'll also see a picture in the next slide. We're going back to the credit card data set. The credit card data set had 7 or so, if I remember right, quantitative ones, and a bunch of them, 4 or so qualitative ones. And one of the qualitative ones was whether a person was a student or not. And this one would resonate, and I'm sure you'd probably be eager. Those data sets, by the way, that the book discusses are real. And so last time we saw that the income or the balance on the card was not sensitive to gender. It didn't make a big difference, was what we saw. And for that period of time, that probably was the case. And so now you would probably be curious on this credit card data set, whether this amount that somebody owes on that card, which is what balance was, is affected whether a person is a student or not. And that's our beta 2. So it will be have a value beta 2 if the person is a student, or it will have a value 0 if the person is not a student. So we are now having this dummy variable that is being included. And so now we are going to notice how it has become now some coefficient, right? Because we are going to have an interaction for it, and that's why it has become a coefficient like this, because we are going to see its effect. And so 0 if the person is not a student, and if we rewrite this one, we will get the expression that you would see. So the interpretation on this one, and this is what balance would now look like. So we had income is what we are trying to see is income and students interaction there, by the way. And so we are going to now see how the interaction term affects the thing that would have been on 1 or a 0 or a beta 2 and a 0. Now we have something that depends on income included in its term if it is a student, and 0 if it is not a student. And the rewriting of it is is shown in the expression below. So remember what we are doing. We are trying to include a dummy variable that shows whether a person is a student or not, but we are going to also include the effect this has, the interaction between income and this dummy variable or this Boolean variable we have, whether that shows whether it is a student or not. And the expressions came this way. So for this particular data set, this is the place where I want you to pay close attention and be happy that you're a student. What you see on the left, and I'll tell you why you should be happy. What you see on the left is the thing that doesn't pay attention to interaction. And so we've got the red, which is student, and the black, which is non-student. And what is being plotted here is your income and balance. Income, as it increases, the balance on the card increases, is what it would say. So people who have a lot of income would probably accumulate lots of credit on the card. And so they have got many things to pay, is what that would say. And it has got some coefficient to it, that slope. When it is not student, you've got that picture. The only difference between the two was the intercept, because there was an offset. And that was what the model, without the interaction, would have told us. What you see on the right is when interaction is paid attention to, the interaction between being a student and the income. And now the picture changed. It's not only the intercept, but slope also changed. And you can see that the one that has got student is kind of lower slope than the other one. And this means you're not, as these other non-student ones that have a lot of balance, the balance what the students had when that income is accounted for is a slower rate. And that's the reason why you should be happier, because you are not accumulating a lot of balance on your credit card, says the data, not me. All right, that was the end of the things that I wanted to discuss around interactions. And we have seen both when things are quantitative variables and when things are qualitative, or a mix of them. The other extension we want to make is when there is non-linearity in your model. And this would take us to a data set that you've seen in one of your assignments, and it will come again in another assignment, or in your last assignment. I think we will make room for it. This auto data set has got many things, but one of them is miles per gallon. You may remember in your assignment you have plotted. And so if you were to plot miles per hour and versus horsepower, and these are the data points you have, you can see what the orange one does. The orange one is what we've learned so far. You've got these predictors, and you are assuming there is a linear relationship. And you can see now that it is not doing all that great a job, because it's kind of away from some of these points. You can do a better job. This data set, this thing became like this because the relationship is not linear. So we're trying to force a linear model on it when it is not linear. And so we have a way to increase the polynomial of the method we are using. So the linear model could be of degree 1, is the way to interpret it, is each of the predictors is just as it is. That's why it's a degree 1. So if we were to include a higher degree, we still can work with our linear model and capture that non-linearity. The curve that you see in green or in blue, I think it's blue is what it would be, is a degree 2, and it does a better job. It does a better job capturing the non-linearity. If we say, okay, we're tempted now, we're going to go higher and higher, and we make it to go all the way up to degree 5, we come to a place where we will call overfitting. This became wiggly. They're trying to trace all of these variations in the data, and as a result of it, it does a poorer job than what the degree 2 does. But the picture tells us now the linear model was not a good fit for this one, and we could do better by having one more power. And the way to do this is like this. And now we are making it simple. We are looking at one response variable and a predictor for it. And the predictor for it is horsepower. And what we are trying to predict, or the response variable, is miles per gallon. And so in the absence of anything else, or when we are just happy with a linear model, we would have said beta 0 plus beta 1 times horsepower, which is what the variable is. And we would have gotten the orange one. We got the better one by having to introduce a new term that was not there. And this one is taking horsepower squared. That was why it was degree 2. So this variable is something we introduced, and it is of degree 2, and it is literally squared, and we get a coefficient for it. Now, the reason it's called higher degree is because we introduced a variable that is of higher degree. The reason we still call it a linear model is because it's linear in the parameters, which is what this the result of your model will tell you. So the betas are still linear, and the variables are the ones that are in of higher value here, and we stopped at degree 2. And R, as we will see next time, will give you some more systematic ways to try out different degrees, but this is what you would get with degree 2. If you wanted a degree 3, you would have a third coefficient for it, and you will have horsepower cubed, and every time we have something like this, we should also have the error term in it included. So what you see here is it helped. It helped because the new variable horsepower squared has got a p-value that's so small, which means that this is strongly significant. So you've got a way to assess whether this one is doing well or not. Okay, as I told you, today will be to finish this discussion around linear regression. And we've got a few topics left, and I'm going to use the rest of the time to highlight some of these. And I'm going to also remind you, if you wanted more discussion around this, where to read in the book. But let me see if anybody's got any questions on what we have so far. So we're going to face 5 problems. I don't know if this is a good way to motivate you. We're going to face problems, but we are going to have a slide on each one of them talking about how to deal with them. So that should make you happy. So these are potential problems other than the ones that we have seen so far that we need to deal with when we have a regression problem. And our tool is a linear model for it, and what we do with them is what we will do. These are real problems. These are issues that show up, and so we better know them. But anybody's got any questions for me so far? Okay, can I get a thumbs up or somebody saying I am following along? Thumbs up or saying yeah on chat or something like that. I got it. Okay, I got a few thumbs up. Oh, I've got plenty. Okay, I'm going to go ahead. Thank you for all those thumbs ups. All right, let's see one of these at a time. Non-linearity, we've already talked about it. There are some data sets for which a linear model is not a good way to capture it. But how would you find out that your problem has got non-linearity in it? Is there a way for us to see that more quickly? And there is. And this is obtained by having to plot residuals. Remember, those residuals were the predicted value and your estimate, or the actual value and so on. That difference was what the residual was. And so you could, and you could do this for every single one of your n terms, your data points. If you were to find that residual, the error you made, and you plot it against a fitted value, you get a plot. And so the plot you see now on the left shows you one of those. And in fact, this one is for the auto data set that we just talked about, which we already know is non-linear. And we found out after we did the linear model to see how it improved because the p-value was great. And we also saw the original one that was plotted that kind of gave us. But is there a pattern that we could recognize that would make this one evident? And that is what this figure is showing you. When it is nonlinear, you see the thing that you see, the red curve now is a fit to this plot. So the plot is residual versus fitted values. And if you do a fit on it, you get something like this. And that one is supposed to, when it is linear, not to have variations. You expect all of these residuals to kind of be the same way, but now it's not. It's actually a U curve. And if you see that, then there is evidence for nonlinearity. What you see on the right is when you have turned it into, you introduce that horsepower squared term, and now you can see, you do the same plot, and you now see, you don't see that pattern. So that means now you could feel better because now you have captured that one. This type of plots R can do for you, or most other packages would do for you. And your exercise, your assignment 5 will make you do something like this. Okay, you can see how they are behaving, whether what you did makes sense. Okay, nonlinearity, that's covered. The other problem is about correlation of error terms. And I would invite you to read this one in the book, and it should not take you very long, but I'm going to spend just one slide to tell you what this means. When you have things like time series data, for example, you are taking this, a time series data will be on discrete times. And so you have sensors, and so they told you how much, whatever it was, at this time, at this time, at this time, or your heartbeat, or whatever it is that the time series, or the economy, or whatever, on a finer or broader time scale. If you think about it, there is a good chance that the error that you would see when things are close by could be more correlated than the error you would see if things are far apart. And so if it was a faulty sensor, then whatever it was reading was at time ti, and time ti plus 1 is most likely going to be correlated because that same sensor that's giving me this anyway. Or if it was an event that has happened, whatever the error is has a tendency for it to be correlated because of its closeness. And so here are three plots. The three plots are when you have a factor rho that would show you when there is no correlation, a factor that would show you when there is half a correlation, and something that shows you when there is a 0.9 correlation. And you can see when that correlation is a 0.9, the points that are close by are so close to one another. You have to adjust for this. You have to deal with this. This is a way to see them, and correlation between error terms could be a cause for your linear model not to be a good predictor, and its R-squared value at the end or other things could capture that and would show you. And so this is a way to deal with them, to find out and to deal with them. Okay, problem number 2 addressed. Problem number 3 has to do with outliers. And I'm going to talk about outliers in this way. And I'll show you 3 pictures. The first picture shows you something. Something is a y is a response and x is a predictor for it, and you've got these measurements and or some things that you have done. And if you look at data point 20, it is way out from the other ones. It is an outlier, as you can see. And what you see on the red curve, I'm talking about the plot on the left, y versus x. What you see on the left curve, the red curve to those data points is a fit, a linear model that you have done when everything is taken into account. So that outlier, the presence of it, and if we were to remove it, is not going to so very much affect what the fit was. And so the broken line that you see shows you when the outlier is removed. And the red curve shows you when it is not removed. So it didn't make a whole of a big difference, but it was an outlier. But there are times when an outlier may affect your value. So when would you send? Then you could say, you probably would be better off if the outlier was affecting it to remove it. Otherwise, it's just causing you a problem. You have all these things that would, tend to tell you one story, and here comes an outlier, and probably it was even a mistake, and it's going to drive your model the wrong direction, and you don't want that to happen. And so in this particular case, its removal didn't make a big difference. So when would you decide whether an outlier should be removed from your model or not? Because a visual view like this will not probably be telling you. A better thing could be obtained if you were to plot the residuals against the fitted values. We've seen something like this before. And now you see the 20 coming out even more dramatically outside what you would expect for these residuals. That was great, except for one thing. If I was going to do this, then when am I going to decide whether something is actually an outlier or not? To reject it, to take it out of my model. You do that if you normalize. These sort of things happen most of the time in statistics, or in other things too. In fact, in anything that involves metrics. So if you have taken my network science class may remember different centrality metrics or things like that we use to measure how a node is important in a network, for example. If you just go by numbers, it's kind of difficult. When am I going to say something is important or something is outside the range or something like that? You better come up with a way to help you normalize it so that now you are independent of the data set that you're working on, how many n's you have and things like that. The studentized residual plot is what you see on the right that gives you that. Data's got some numbers that you have to divide by something else, normalizations written in the book. The more important point is now you have a way to know when something could be declared an outlier and is good to remove it from your model. If it's value, that's studentized residual. If it is between -3 and 3, it's okay to keep it. If it lies outside of those, that's a candidate to throw out. Outlier that destroys your model from behaving the way it should with the rest of the model. You have a way to detect it, and you have a way to avoid it. Okay, just like we have seen outliers, there are things called high leverage points. These are points on the predictors that kind of heavily influence what the linear model would be. The guy in the example here, yx is the same thing that we have seen before, not the same thing, but the same idea, that is have high leverage point is the x4 value. And you can see that was 41, data point 41. The 20 was the outlier. It didn't make a big difference. But the 41 made a big difference if you look at what the red curve is. That is the one with everybody included. And the broken line is when this particular data point is excluded. And you can see the model now significantly changed. Data points that influence your model in one direction, like this, by having a lot of leverage, are called high leverage points, and 41 is one example to do that. Just like the residual was a way to show us this, we could see the pairwise. In this case, we are going to look at a pair, just two predictors, x1 and x2. And if you plot one over a pair, this plot that shows you how they relate with one another, most of them kind of are about the same value, right? Because now this x4 was significant because its value was so high. That was why it was changing it. And you can see now that 41 has come out of this range in a big way. And this is how you would identify leverage points. And their inclusion and exclusion will be something that as a domain expert, you would want to evaluate. Maybe you would need to keep them, but then say, okay, here I have this thing in my blood sample has got this greatest effect on this thing, and so I know for what it is. But if it was something else, then you probably would be better off downplaying that leverage point that this one has. And so that type of assessment can be made by looking at a plot like this. That was my point. The other point I want to make, and I'm going to make this one a quick one, is when variables are collinear. Most people you have talked to might have said this, or you might have heard people talk on TV, this thing and this thing are collinear. That means there is dependency between the variables. And so they are going to mess up with their model to some degree. And we will look at this notion in some related way when we talk about unsupervised learning and we do principal components analysis. But I've got a few points that kind of advise you against or help you know about co-linearity, what it means and how to deal with them and how to quantify them. So the notion simply means a predictor value has closely related to one another. And you could find out if this is the case by by computing the correlation matrix of the predictors. And this value, the elements in this matrix will have large in absolute value. When they are large in absolute value, would tell you that these things are highly correlated. It could also be the case that you've got more than one. I have not seen too many examples of that type unless you really are dealing with some complicated physics or some other phenomenon where you have really, 3 or more variables to be correlated. Most of the time it will be 2, but you could also have in the presence of, wide data, as it's called now, when you have many predictors collected. Why are they collected? By the way, you should also pay attention to that. I'm not sure if I have emphasized this enough times. The reason we have wide data, as many predictors, is because we are able to collect them. And so sometimes we have got this and that and this, and we don't know which ones will eventually be helpful for our machine learning problems to solve, and we keep them. Why? Because we have them, and we sometimes become a victim of that because we've got too many of them, and they were collected just because we could. Somebody was clicking on a video, and they were doing that, and so we had log, and so it were indiscriminate, and so there could be many. And so if you think of those types of data sets, you wouldn't be surprised if you have more than 2, 3 or more variables that are correlated. And so it's not as rare as I am trying to make it out now that you have this, but you have a tool. When it is 2, correlation would tell you, and when it's 3, with some more effort, you could get this also, and they are called multi-collinearity. I'm not a big fan of terms. Hierarchy was the first thing that I told you. For example, if the interaction variable contributes, keep the parent one also. If you call it hierarchy, okay, call it hierarchy. But the thing that needs to be done is what is important for me, and I would like you, but you also need to communicate to others, so maybe you should know them. And so this is called multi-collinearity. Okay, there it is. When you have more than 2 things that are correlated. I have a term called variation inflation factor that is a better indicator when you have multi-collinearity. Correlation by nature has got 2 things, and so the correlation matrix is a good indicator. When you have many, you have got this factor that you can compute, and you can see the details of that in the book, what that means. All right, I am going to use my last slide. This is my last slide to tell you what I began off telling you, that we are learning about linear regression because it's a method to use when we have a regression problem to solve. It's a simple method, but it is powerful enough. And in many ways, especially when you have careful enough for the kind of things that we talked about, when you're careful enough about non-linearity and things like that, that's probably all you really need. But I also said that I wanted you to have this discussion on linear regression because we have a need for it in terms of other methods. And these are generalizations. And this book has got a good example. And as much as our time allows in this course, we would see examples of them. The first thing we will encounter is when we start the topic of classification next week. One of the first methods we will learn is called logistic regression. The regression there is right there. And so we will see why it's logistic. And it is an extension of the linear regression theory we have. Support vector machines is another big class of classification algorithms, and that relies on linear regression, the concepts we have learned. We're not going to spend time talking about support vector machines in this class, but that's one. Non-linearity is, we dealt with it within the linear model, but there are other ways. Splines, generalized additive models, or kernel smoothing, these are all ways in which the linear regression theory we now learned would be extended when problems are non-linear. The interaction one is a bit curious. I am going to talk about tree-based methods for sure. When we talk about classification, we will see them, and we'll talk about random forest and bugging. Really, what is happening there is you're taking this interaction between variables to even a higher level. So the interaction I told you was so simple for us now to say, I'm taking the product of these two. But when you really wanted to have more of their interactions captured, this is what ensemble methods would tell you. These are more sophisticated and they're very powerful methods. And so knowing about this one now will give us a good way. The last one is kind of funny. It's funny because we say, linear regression is not capturing non-linearity and we have to fix it this way and that way. But sometimes it could be even more powerful than you really need for some problems. And so we'll have to take another way to regularize this fitting. And there is a large class of machine learning problems that would fit into that. That you would benefit if your understanding of linear regression is a good and solid one. I hope that is what we have achieved. I'm not going to claim that we have a solid, great foundation, but I think this was a good review and a good introduction for those who needed it and a good reminder for those who know about it. And so Friday, we will have a session where we will look at codes. And I'm going to stop here. All right, it is 10 o'clock. I'm going to stop here and I will see you on Friday. And for some of you, I'll see you during office hours today.